Hello, I'm Adrian Miranda, and today I'll be talking about the Decalage comonad and its restrictions. So the Decalage comonad is a comonad on the category of simplicial sets. So recall that a simplicial set has a set for every natural number n, and it has various face and degeneracy maps, as indicated with the D's and the S's respectively. And the decalage construction acts as a dimension shift. So what it does to a simplicial set is it creates a new simplicial set whose n simplices are the n plus 1 simplices of your original simplicial set. And it shifts the indexation on the face and degeneracy maps down as well. So what happens to the face and degeneracy maps that will necessarily need to get discarded? Well, they become the co-unit and co-multiplication of this comonad. So the co-unit, as you can see, involves the face maps that we need to discard when we shift down a dimension. And similarly, the co-multiplication involves the degeneracy maps that need to be discarded, as shown here. So in this diagram, we can see the comonadic adjunction involved with the decalage comonad. And we can see that it actually restricts to the full subcategory of simplicial sets on nerves of categories, or CAT. And when you do restrict it there, the induced Coe-Lindbergh-Moore adjunction is well understood. So the coalgebras are categories with local terminal objects. So that means a terminal object in each connected component. And recall that taking the decalage of a category, when you do that, the new category that you get is the sum over the slice categories of your original category. And also that the terminal objects in each of your connected components are actually the identities of the object corresponding to that slice. Another aspect that we will need to keep in mind about decalage on categories is that to give the structure of a coalgebra on a category, you need to give a right adjoint to the projection from your category to its set of connected components. So this, these kind of intuitions from decalage on categories will help us when we next look at decalage on two categories. So recall that the category of two categories and normal lax functors is also a full subcategory of the category of simplicial sets. So the Duskin nerve of a two category has 0 simplices the objects of your two category, 1 simplices the arrows of your two category, 2 simplices are certain triangles as depicted, and note that they're not commutative triangles anymore, but rather there's a 2 cell sitting inside that triangle. And then 3 simplices of your two category will be certain commutative, well, there'll be a commutative tetrahedra inside your two category. And also note that two categories as simplicial sets are 3 co-skeletals. So all of the higher dimensional information can be kind of recovered from this information that I have given here. And the maps that we want to consider between our two categories aren't the usual two functors, but rather they're normal lax functors. And so these are like two functors, except they only preserve composition up to some coherent non-invertible 2 cell as depicted in this picture. So these are precisely the morphisms of simplicial sets between the nerves of two categories. So the decalage of a two category, very similar to decalages of categories, is taken as a certain coproduct, and it's a coproduct now over the lax slices of your two category. So what is the lax slice of a two category? Well, its objects are going to be the arrows of your original two category, but then an arrow in the lax slice is going to be a certain 2 simplex in your original two category as depicted. A 2-cell, however, in your lax slice will still be a 2-cell in your original 2 category, but it'll be subject to a certain commutativity condition as depicted as well. So the question then is, what are the coalgebras when DEC is restricted to 2 categories and normal lax functors? So I'm going to give 2 characterizations of these coalgebras, and they'll both be having a similar flavor to the characterization of coalgebras when DEC is restricted to cat. So one way to characterize a 2 category with a Decalage coalgebra structure is that it has some object in each connected component. So I'm writing that as big I sub little I, where little I is an index telling you which connected component of your 2 category we're in. And then, as well as that, you need a terminal object in each HOM category into that object. So if X is in that same connected component, then the HOM category KXI should have a terminal object. And then on top of that, you need to satisfy the condition that the terminal object in the endo-HOM category on your chosen object needs to also be the identity. So this structure satisfying that property precisely characterizes coalgebras for Decalage restricted to 2 categories. Another way to characterize them is via a section to your projection to the connected components, and not an adjunction, so not literally a right adjoint to that, but rather something that kind of looks like a right adjoint. So you still have a 2 functor from pi naught of k back to k. And then as a unit, you now have a lax natural transformation. And here what we will ask for is a lax adjunction with identity triangulators. So normally with a lax adjunction, you ask for not necessarily even invertible modifications over here, which you would call triangulators, and then you would ask them to satisfy certain tetrahedral identities. But here we want our triangulators to be identity modifications, and the tetrahedral identities, which aren't trivial, but we do want them to hold. So we do want it to be a lax adjunction with identity triangulators. Okay, so just for a little bit of intuition, the lax naturality constraint. So first of all, the component of our lax natural transformation will be the chosen terminal object in our HOM category. And the lax naturality constraint on a morphism will be the unique map in that HOM category to the terminal object. Okay, so now let's talk about some examples of 2 categories which do have this structure. So first of all, you can consider the dual. So we're going to be dualizing the 1 cells and the 2 cells, but the dual of the category of monoidal categories and lax functors. Okay, so its chosen object, so it's a category with 1 connected component, and its chosen object will be the terminal object, right? And we're going to be HOMing out of that, and that when you HOM out of that via the lax functors, the HOMs are going to be precisely monoids in the monoidal category that you're HOMing into. And recall, of course, that the category of monoids in any monoidal category has an initial object given by the unit for your monoidal structure. Okay. Then there are many examples that come from Cartesian bicategories. So for example, T-span E for a category with finite limits E and a Cartesian monad on your finite limit category. Then VProf for monoidal, so semi-Cartesian monoidal categories. So that's when your unit is actually a terminal object. And then there's another example, the 2 category of restriction categories and restriction functors. So I'm not going to recall for you the definition of a restriction category, but with a restriction category, for each object, you have a meet semiladders of restriction idempotents. And so that will actually define the terminal object in our HOM. And the chosen object will be the restriction category of meet semilattices and stable maps. Thank you for listening to my talk.